Okay, so here we take a look at the nitration of benzene to form the liquid product, nitrobenzene. I'll also take a look at the stages in the purification of nitrobenzene. In the round bottom flask there, which is sitting in a trough containing iced water, I've already prepared my nitrating mixture. That's a mixture of concentrated nitric acid and concentrated sulfuric acid. Dripping into that very, very slowly from the funnel above, I'm adding my organic reagent, benzene, colourless liquid. I keep a thermometer in there to ensure that the temperature never goes above 50 degrees centigrade. If the temperature does go above 50 degrees centigrade, I'm likely to get multiple nitration of the benzene ring, forming dinitro or trinitro benzene instead. The process then takes place slowly. In this case, it took me almost half an hour to add all of the benzene to the nitrating mixture. And of course, bear in mind that trinitrobenzene is a near relative of this chemical, TNT or dynamite. So you have the potential for forming explosive byproducts in the reaction if the temperature rises above 50 degrees C. So as I said, this took me about half an hour roughly to get all the benzene in while keeping the temperature below 50 degrees centigrade. And of course I would shake the flask from time to time to mix the reagents together well. And there you see at this stage most of the benzene has been added from the funnel to the nitrating mixture, so this is about a half an hour later. And I should have their nitrobenzene in the flask. Let's consider the mechanism. It's known as electrophilic substitution, and there's the electrophile, the NO2 plus ion, or nitronium ion, formed by the reaction of the two concentrated acids in the nitrating mixture. Look at that circle in the middle of the benzene ring. It represents 6 delocalized electrons. And this curly arrow shows that 2 of those 6 electrons come out to form a bond between the benzene ring and the NO2 group. Watch then how the bond between the benzene ring and the H breaks. The hydrogen leaves behind its electrons, so the 2 electrons go back in to complete the ring representing the 6 delocalized electrons. And there's our product, nitrobenzene. And if you like counting your electrons here, the ring there in the intermediate has a positive charge because it's sharing 2 of its 6 electrons. And sharing 2 electrons means it's effectively down 1 electron. To get the maximum yield of nitrobenzene, it is necessary to carry out mild reflux distillation for about 45 minutes, which you see I'm doing here. So you set the reaction mixture up as shown here with the Liebig condenser placed in a vertical position. The flask is sitting in a water bath kept at around 60 degrees centigrade. There's a thermometer in the water bath there to monitor the temperature closely. The water goes in at the bottom of the condenser there and out at the top. The rule is that water should flow uphill. You won't actually see much happening in the flask at this stage. It's not bumping or anything. But the temperature is maintained at around 60, as I say, to produce a higher yielded product, nitrobenzene. The flask is taken out from time to time and given a good shake to mix the 2 layers together. In other words, to mix the organic reagents with the nitrating mixture. And I've speeded it up here, so we'll go to the end of the 45 minutes and move on to the next stage. I allowed the contents of the flask to cool to room temperature, and I then poured the mixture into an excess of cold water in this flask, and this is what you see here. My product, nitrobenzene, is present there at the bottom of the flask. The mixture in the flask is shaken and stirred vigorously. This is so that the water will remove as much of the acids as possible from the organic reagents. The layers are allowed to separate, and then I decanted off most of the upper aqueous layer. And what's left in the flask now, which includes the product, will be transferred to a separating funnel. And this is of course solvent extraction. The acids will be more soluble in the polar water layer than in the organic layer. So most of the acids at this stage will transfer into the upper aqueous layer, the polar layer. So when all of the liquid mixture has been added to the funnel, it will be left to sit to allow the layers to separate. And again, I'll speed the process up. It did take several minutes for this to happen, for the layers to separate fully. I then separated the two layers, and here you see I returned the lower layer, my product layer, back to the funnel and added about the same volume of water and give it a good shake. And the funnel is then left to sit to allow the layers to separate once again. And you can see there, this is again speeded up. You can see that the nitrobenzene is forming as the lower layer once again, being more dense. This process will have removed more of the acid that is contaminating our product. The acids will move from the lower product layer up into the aqueous layer above. And once again then, when the layers have separated, I separate the layers. The lower layer is my product layer. And as you get near to the interface between the two layers, it's necessary to slow the rate down. And there you go. I've separated the two layers, and that's my product there collected in the flask. There will still be some acid present in that, and the next stage is to wash the product by returning it to a clean funnel and washing it with sodium carbonate solution until there's no further evolution of carbon dioxide. Remember that acids react with carbonates to form a salt, CO2 and water. And if there's any acid in there, when we add the sodium carbonate and shake it, we will see effervescence. So when there's no further effervescence upon the addition of sodium carbonate, that means that all of the acids have reacted. Now, of course, we will have replaced the acid contaminants with a sodium salt, sodium nitrate, sodium sulfate. But ionic salts will be essentially insoluble in the non-polar product layer. And so they will be dissolved in the upper aqueous layer and will be removed. Here you see I'm shaking with the sodium carbonate solution. It's necessary to remove the stopper to let the gas escape. And one can add a few cubic centimeters of sodium carbonate solution at a time with shaking and allowing the gas to escape until there's no further signs of effervescence. And again, you can see the funnel is left to sit, and time is allowed for the layers to fully separate again. In order to remove any water that may be contaminating the product, it's transferred to a conical flask and shaken with anhydrous granular calcium chloride until it goes clear. Then the final stage of purification is to carry out simple distillation and collect the fraction that boils between 207 and 211 degrees centigrade.